Thanks, and good morning, everyone, and welcome to Code as a Crime Scene. Today, I want to give you a different perspective on your code base. I'm here to investigate the traces we all leave behind as we create our systems. And you will see that there's a lot of valuable information in those traces. It's information that will help us predict the code that's hard to maintain, the code that risks for defects, and the code that becomes a team productivity bottleneck. So let's jump right in and have a look at what we programmers actually do. We programmers, we don't write code. Yeah, sure, we do that as well. But that's not where we spend most of our time. If you look at the research, you will find that we actually spend the majority of our time making modifications to existing code. And most of that time, in turn, is spent trying to understand what the code does in the first place. And what that means is that if we want to optimize any aspect of software development, we should optimize for ease of understanding. That's where the big win is. This is a challenge. Here's why. Please have a look at this visualization. I will claim that that's where most code bases eventually end up. It's pretty complicated to reason about. Which parts are hard to maintain? Where will the bugs be? Are there any team productivity bottleneck? Without more context, we just cannot tell. And this is a problem that gets harder with the scale of it, because today's systems are developed by multiple programmers organized into multiple teams. And that leaves everyone with their own view of how the system looks. No one has a holistic picture. And this is not a new problem. This is a problem that's been around for decades. And we do have a number of traditional solutions to this within the software industry. So I'd like to start this talk by having a look at some of the traditional approaches to tackling those problems before we see the limitations of those, and then we move on to something entirely different. So if we want to know which parts of a code that are hard to maintain or complex, why don't we just measure it using complexity metrics? So let me ask you, how many of you have been using complexity metrics of any kind? So few of you, maybe 7, 8 people. Great, thanks. So we actually have a number of different complexity metrics to choose from. And this is just one example. This is one of the most popular approaches. This is called McCabe Cyclomatic Complexity. And what you do in McCabe Cyclomatic Complexity is basically you consider your program or your function as a graph. And then you calculate the number of possible paths through it. And then you sum up that number, and the higher that number, the more complicated your code. And this kind of makes sense, because it ties back to one of the most limiting factors we have in programming. It's a cognitive factor. It's our working memory. There's really just so much you can hold in your head at once. So I would say that McCabe definitely makes sense. Why don't we use complexity metrics more? I don't know, but I know the reason that I don't use them. The reason I don't use complexity metrics is because complexity metrics are pretty bad at predicting complexity. Perhaps a bold statement, so let me support that with a quote. Syntactic complexity metrics cannot capture the whole picture of software complexity. And what I like about this quote is that it's from a research paper. And what the researchers did here was that they took a number of different complexity metrics, McCabe was one of them, and then they applied them to real-world code bases and looked at how well they perform. And what they found out, and this was really, really interesting, was that as soon as they started to control for the number of lines of code, those more elaborate metrics that didn't add any further predictive value. Wow. The number of lines of code? That's a lousy metric, isn't it? Is that really the best we can do? Let me read another quote for you. This is one of my personal favorites, because this one is a little bit evil. The use of metrics to manage software projects has not even reached a state of infancy. And this is a quote by Robert Glass, one of my favorite authors. If you haven't checked out his books, please do so. He's great. And what Glass means is that software projects, they are so complicated and so open-ended, so multifaceted, that we will never be able to measure it. So what Glass claims is that we should do something different. We should use our intuition. Now, as some of you may know, I actually have a parallel career as well. I have a parallel career within psychology. And as a psychologist, you just have to love the concept of intuition, because it's such a warm, fluffy human subject. But what is it actually? Well, let me ask you, how many of you have been programming for more than a decade? So half the room at least, great. So during that time, you have all built up a lot of expertise. You know a lot about code, and all that expertise is stored away somewhere in your head. Now, intuition is basically just something in the situation, perhaps something you see on screen, something you see in your code editor, that triggers a recall of some of that information. So intuition is basically just recognition. However, intuition is also an unconscious automatic process. And that means you have no conscious control over what kind of information that gets retrieved. And that's kind of what gives intuition its mythical qualities. It also, like all other unconscious processes in our brain, it also makes intuition quite prone to a bunch of different cognitive biases. And even if we could somehow control for those biases, which we can't, we are hardwired to fail for them, but even if we somehow could, intuition probably still wouldn't do the trick. And here's the reason. Intuition doesn't scale. There's no matter how good we are as developers, there's no way our expertise and intuition is going to scale to millions of lines of code. And the software world hasn't really come up with a good solution to this. And that's why I suggest that we look into a different field. A completely different discipline, but one that faces similar, open-ended, complicated questions as we do. So welcome to forensic psychology. You probably all know a little bit about forensics already. I guess you have read about different crime investigations in the papers. And I'm pretty sure you have seen a number of interesting things on TV, like Numbers or CSI, right? Dexter, anyone? I also bet that most of you have probably seen one of my favorite movies, Silence of the Lambs. How many of you have seen Silence of the Lambs? Virtually half of you, great. How many of you agree with me that Hannibal Lecter is the coolest character? Yeah, he really is. He's amazing. And the first time I saw that movie, I was quite influenced by Hannibal Lecter. And no. No, I really don't mean that in a scary way. I was influenced by his forensic skills, not the other stuff, promise you. And I was influenced by him because if you think about it, it's quite amazing what Hannibal Lecter does. So Hannibal Lecter, he sits there, locked up in his cage, and he receives information from the crime scenes. And based on that information alone, Hannibal Lecter is able to deduce not only the motives, but also the personality of the offender. And when I saw that movie the first time, I was like, wow, I want to learn how to do that. Years later, as I actually started to study criminal psychology, I got terribly disappointed. I got disappointed because it turned out that those amazing techniques that Hannibal Lecter had been using, they have quite a serious limitation. It turns out they only work in Hollywood movies. But fortunately, there are some more scientific methods that we can use. So please allow me to give you a short introduction to geographical offender profiling, which is a modern forensic method. Geographical offender profiling is based on a very fundamental fact. Did you know that criminals, most of the time, behave just like us? They go to the movies, they go to restaurants, they go shopping, they meet with friends, perhaps they even pick up the kids from school. And as they move around in an area, that's where they spot an opportunity for crime. Because for crime to occur, there has to be an overlap in time and space between an offender and a victim. And what that means is that the crime scenes, their geographical locations, are never random. They contain information about the criminal, and that's something we can use to catch them. And I would like to show you how this is done in the real world. And to do that, we need to travel together in time. We need to travel to 19th century London, to the Whitechapel area, the streets that Jack the Ripper haunted. So what you see here is a map over 19th century London. And you see the blue dots on that map with the labels. Each one of them represents one of the crime scenes of Jack the Ripper. Now, in a geographical offender profile, here's what you do. You take each one of those crime scenes and consider them as a center of gravity. And then you weight them all together. But you also add your knowledge of human behavior and psychology into that weighting. So for example, crime scenes that are closer to each other get assigned more weight, because psychologically all distances aren't equal. Now, if we weight them all together, we end up with a new center of gravity. And that's the red area you see there in the middle. That's something called a hotspot. And according to the research, there's a 70% chance our offender will have his home base there. So that's the area to patrol and supervise if you want to catch the Ripper. Now, before we move on and look at how this applies to software, I have to admit that Jack the Ripper, it's a really cheap case study to make, because Jack the Ripper was never caught. So who was he? I really wish I could answer that question. I can't. But what I can do is to take some of the main suspects and look at how well they fit the profile. So let's start with my #1 personal favorite suspect, James Maybrick. James Maybrick was a cotton merchant from Liverpool. And when he went to London to do business, he used to rent a room in Middlesex Street. So let's have a look at Middlesex Street. There it is, right in our hotspot. If you read the news like a year and a half ago, you probably heard about some supposed DNA evidence against another Ripper suspect, the hairdresser Aaron Kosminski. Kosminski used to live at Sion Square. So let's have a look at Sion Square. It's a little bit east of our hotspot. So Kosminski is not as good as a fit for this profile as Maybrick is. But this just raises a really important point that I would like to ask you to keep in the back of your head as we apply this to software. Because a geographical offender profile never, ever points to a precise precision. What a geographical offender profile does is that it projects a probability surface onto the geography, right? So this is all about probabilities. Now, why do I think that this applies well to code? Think about what we have done. What we have done here is that we have taken a potentially vast geographical area and narrowed it down to a much, much smaller part. A much smaller area where we can now focus our human expertise and intuition and manual efforts and still be pretty sure that we will catch the offender. So what if we could do the same in code? What if we could take our code bases with hundreds of thousands or million lines of code and narrow them down to a few hotspots? And still be pretty sure if we actually improve that code, we get a real effect in terms of both productivity and quality. How can we use this in code? Well, the first thing that we need is a geography of code. And this is my favorite approach. This is TeamCity. In TeamCity, software systems are visualized as towns. And each module, each namespace in your code base gets visualized as a city block. And each class, each file gets visualized as a building. And the larger that building, the more complicated that code. So this is something we measure from the code alone. Now, what I like about CodeCity is that it gives us a pretty good overview of the complexity distribution within our code base. However, it doesn't really move us forward. This is just our plain old complexity metrics. Visualized in a novel way, for sure. But if this was all the information I had, I would go after those large buildings and try to refactor them. So to get more precise information, we need to add something. We need to add the missing dimension. We need to understand the spatial movement, not of criminals, but of programmers. And the good news are, that's data that you all already have. We're just not used to think about it that way. I'm talking about the version control systems. Our version control systems are a great behavioral log of how we as developers interacted with our code. And what you see here is a simple example. It's a single commit by a single developer. But you see that each time we make a commit, our version control system records a lot of valuable information. For example, we see who did a commit, when did the commit take place, and the most important piece, where in the code did the change take place. So what I suggest is that if you look at that, that's a single commit done by a single programmer. A large system contains virtually thousands of different commits. So what if we take all that data, aggregate it, and project it onto the static surface of a code? Here's what it looks like. You see those red areas glowing up? Those are our hotspots in code. And in this case, a hotspot is defined as complicated code that you have to work with often. So, complicated code that you have to work with often, what does that actually tell us about that piece of code? To answer that question, I've done a bunch of different case studies, and I'd like to present one of them to you here. This is a case study where I studied a code base over a year and a half, and the code base was developed by close to 100 programmers, and it was a fairly large code base, half a million lines of code. Here's what the geographical offender profile looked like. My wife always claims this looks like an alien, but it's not. This is approximately 500,000 lines of code. And you see that I moved back to two-dimensional representation. And the reason for that is I find that this gives us a much better overview of the relative importance of the different parts. So this is an interactive visualization, and you can zoom in and out to the level of detail you're interested in. But even here, on the highest level view, you're able to spot a number of hotspots. You see those red circles? Now, remember, a hotspot was complicated code that we have to work with often. What does that actually mean? To answer that question, I mined a second set of metrics. I looked at how good are the hotspots at predicting where the defects will be. And the reason I looked at defects was because defects have this really fascinating property that defects tend to cluster. Defects like each other. And that means that in your typical code base, relatively few modules tend to be responsible for most of your defects. So I looked at how good are the hotspots at predicting those defect-dense parts. And what I found out was quite interesting. It turned out that the hotspots only correctly identified 7 out of the 8 most defect-dense parts. Even more interesting, the hotspots only made up 4% of the code, yet those 4% were responsible for 72% of all defects. Or if we turn this around, this actually means in this system that if we improve just 4% of that code, we get rid of the majority of all defects. Of course, given that we don't introduce any new ones. The important thing here is that the hotspots help you take that large system and narrow it down to the parts that really, really matter for both productivity and quality. But once we have found a hotspot, we want to understand a bit more about that code. We want to know, is this a problematic area that we already know about, or is it something that keeps declining in quality? And to see how we can do that, we need to understand how our programs evolve. So have a look at this. What you see here is a picture of a piece of code. Now, I'm well aware that you cannot read the details. And that's not just because I'm a lousy photographer. This is actually deliberate, because I want you to focus on the overall pattern here. And the reason I want you to do that is because I'm pretty convinced that we, as an industry, we know how to write good code. We know what good code looks like. We know about the importance of naming, testability, the solid principles, all that other stuff. So the first version of a program typically looks quite good. Let's see what happens next. Whoops. Get a little bit stained. Not sure if that's a good thing. All right, never mind. Let's see what happens next. Oh no. What's that? Well, let's see what happens after that. Oh no. Oh no. That can definitely not be a good thing. What just happened? What just happened to our code that started out so nice and clean and beautiful, and then a number of small disasters occurred to it? What are those disasters? Well, let me tell you. The first one here, that's a new feature. The second one, that's the typical sign you see of a bug fix done late one Friday just before a deadline. And the final one here, that has to be when the project lead decided to cut the scope. And of course, he changed his mind. So this, my friends, this is basically time happening to your program. This is maintenance, and that's actually a good thing, because it means someone cares about your code. Because remember, each one of those small disasters represents something that someone thinks adds value to your program. So you actually want that. You want to see that happen. However, the bad things start when we continue to build upon that shaky foundation, when we allow our programs to continue to decline in quality like that. So what we want to do is to devise a technique that will allow us to catch offending code like that. Here's one way of doing that. This is something I call complexity trends. And complexity trends works like this, that I take each of the hotspots that we identified in the code base, and then I scan through the source code repository. I pull out each historic version of that hotspot and measure the complexity of that historic revision. And that allows us to plot a trend in time like this, which in turn allows us to predict the future. And the data that you see here is real data from real system. This is from the open source project Mono, the initial open source CLR port. And this shows the data for a single hotspot over 4 years of time. And you see that this code has just kept accumulating complexity. It becomes worse and worse over time. Now, remember, it's a hotspot because we will need to work with it often. What do you think happens if we have complicated code that we need to work with often and it becomes more and more complex? It's not a wonder that there's a strong correlation between hotspots and defects. All right. So far, we looked at the technical side, but large-scale software projects, I would claim that the social side of software is even more important the larger the project. And I would like to introduce this segment by one of the best observations I know about software development. Code doesn't lie. If we want to know how something really, really, really works, we need to look into the code. Because the truth is there, and it's described in very precise technical detail. So, code doesn't lie, but it doesn't tell the whole truth either. And if we limit ourselves to what's visible in a static snapshot of the code, we miss a lot of important information. One key piece of information that we miss is something that I call temporal coupling. And temporal coupling is interesting because temporal coupling is quite different from the way we typically talk about coupling in software. Because temporal coupling isn't measured from code, it's measured from the evolution of code. So let me show you a simple example here. What you see here is a simple system with just 3 different parts. The first time I make a commit, I change the fuel injector and the diagnostics module together. The next time I make a change, I change something else. The third time, I'm back to changing the fuel injector and the diagnostics module together again. Now, if this is a trend that continues, there has to be some kind of relationship between the fuel injector and diagnostics module because they're changing together over time like this. What kind of relationship could that possibly be? Well, let's look at some of the most common findings. What you will find quite often when you investigate temporal coupling is this, that you have a piece of code over here that uses a piece of code over here. And each time you change that API, you need to change the client as well. So this is basically our plain old physical coupling. And this is indeed something you can see in the code alone. But remember, temporal coupling isn't measured from code. Temporal coupling is measured from the evolution of your code. And that means you will sometimes come across cases like this, where you have a piece of code here, you have another piece of code here, and there's absolutely no dependency between them, yet they keep changing together over time. How can that possibly be? How can two independent pieces of code keep changing together over time? Is that some spooky quantum physics thing? Most of the time, not. What I will find in most cases is a dear old friend, copy-paste. So you have some code over here, you copy-paste it here, here, and here, and now each time you modify the original, you have to remember to modify the copies as well. So temporal coupling is a great way to detect software clones. But we can do even more with temporal coupling. And I would like to show you how, by showing you how you can analyze a complete architecture. So consider this simple system here. We have 3 different subsystems here. And we can measure temporal coupling on a subsystem level as well. We don't have to limit ourselves to individual files. And if we measure temporal coupling here, we see that these 3 systems tend to be changed at the same time. Now, do you think it makes a difference if those 3 systems are in the hands of a single programmer, or if they're developed by multiple programmers organized into different teams? I was actually in that situation a while ago, so let me share a little story with you. This is something that happened 5-6 years ago. At that time, I was working as a consultant. And I joined a new assignment. And my first day there, I got assigned a number of tasks. So I picked one of the tasks, obviously the one that looked the most fun, and started to work on that one. Pretty soon, I noticed that in order to complete this task, I need to make a tweak to an API. That API was owned by a different team. So I walked over to their team lead, and I asked her, do you think you can make this change to this API? And she told me, yeah, sure, it's a simple change, so I get started with it right away. Excellent. So I went back to my desk and started to work on another task. And that was a good thing, because it took me 1 week to get that simple change. I didn't think much about it at first. I guess something else obviously came up. But it turned out that we had to modify that API a lot. And each time we had to make a change to it, that change took at least 1 week. So one day, I just had to find out what's actually going on here. So I walked over and I actually asked the team lead, sorry, what's going on here? Is something unexpected turning up all the time because it takes such a long time to get that simple change? And what she told me completely changed how I view software architecture. Because it turned out, yes, it was a really simple change for them to make. But in order to do it, they had to go to yet another team and change their API. And that team, in turn, had to go to yet another team. And that team had to go to the database administrators. And as we all know, that's where all change requests go to die. So the takeaway here is that if you have a system with dependencies between its different parts, and those parts are developed by different teams, well, what you actually have is a dependency between people. And of course, this goes all the way back to one of those famous and well-known observations on software, Conway's Law. So I guess you already heard a lot about Conway's Law at this conference, so I'm going to keep this really, really brief. Who's familiar with Conway's Law? Cool. So Conway's Law is basically the observation that the way we're organized as an organization will be reflected in the kind of software we design. And the best thing with Conway's Law is that there are just as many interpretations of it as there are blog posts about it. So we can basically pick our favorite. And my favorite is Conway's Law in reverse. Because used in reverse, Conway's Law becomes a useful organizational tool. So that basically means we start with the kind of system we want to build, and then we'll look at that system and see how should we organize in order to make that happen as efficiently as possible. But yeah, new systems. Most of the time, we have existing code that we need to maintain. We have existing systems that we need to improve. So how can we use Conway's law on legacy code? What I recommend here is that we start by understanding how well does our current system support the way we work with it. And one technique that you can use is something I call social networks in code. Again, social networks are measured from the evolution of your code from your source code repositories. So what I do here is that I scan the source code repositories, and each time I find a file where two programmers have made contributions, those two developers, they get a communication link between them. Now I continue to scan through history, and I find that another programmer has made contributions to the same file. Well, then she gets a communication link as well. And over time, this allows us to build up a complete graph over the ideal communication paths in our organization. And I say ideal paths because there's obviously, this is measured from how the code was actually created. There's nothing here to suggest that some of those lines represent communication that actually took place. So what you need to do now is to take your graph, your communication network, and compare it to your formal organizational chart. And any discrepancies have to be understood. So let's have a look at some typical examples on what you can expect to find when you do that. According to Conway's law, we should expect to find something like this. What you see here is that we have 3 different teams. And you see that most of the communication paths are between members on the same team. And again, that means that on each team, the people work with approximately the same parts of the code. And this is a good thing, because it means they share the same context. And sharing the same context is something that just makes communication so much easier and cheaper. So this is where you want to be. And you also see that you have the occasional line here between different teams. And that's probably also a sign that cross-pollination of knowledge is a good sign in programming too. So that perhaps just represents a programmer that rotates teams. Now, I have a confession to make. All data that you see in this session is real. It's from real systems. All visualizations are from real code bases, except this one. And the reason for that is, as part of my day job, I've analyzed hundreds of different code bases, and I'm yet to find an organization that are that well aligned with their code. So I had to make this up. The next one I will show you, however, is real. So now we have seen where we want to be. Shall we look at the opposite side of the spectrum? How many of you want to see a complete disaster? All right, let's have a go at that. So this is a story about a company. And this is a company, they were in a pretty good position. They were going to do a new product. And they were in a good position because they had done something very similar in the past. So they actually had data that told them that this project, using your 5 in-house developers, will take you approximately 1 year. Yeah, I know what you think. A software project, that's predictable. Ridiculous. And indeed, of course, someone came up with the idea that, yeah, 1 year, but you know, we have this really cool trade show in just 3 months. Can't we do it in 3 months? Now, how do you take something you know takes 1 year and compresses it down to just 3 months? It's so easy. You just throw 4 times as many developers on it. And this was a fast-paced project. The initial architecture was already set, and in shorter time than it would take you to read the mythical man-month, they recruited 25 consultants and chose to organize them into 4 different teams. How do you think their communication diagram looked? What I want to show you now is the real data that I've been allowed to use from the real project. I've just made it anonymous in order to protect the guilty. So here we go. Looks pretty cool, doesn't it? But let me assure you, there's nothing cool about this. This is a complete disaster. This is anarchy. This is a communication breakdown. And the reason it's so bad is because, yeah, if you look at those 4 different teams, you see that the members on the same team, they do have a lot of lines between them, which means they work on the same parts of the code. The problem is that everyone else get that as well. So this is not 4 different teams. This is virtually one giant team of 29 developers with artificial organizational boundaries between them. Now, I didn't work on the project myself initially. I came in as part of the post-mortem analysis, and I got to talk a lot to the developers, and they told me a lot of interesting things. One thing that they told me was that they had a lot of defects. The second thing that everyone told me was that the code was hard to understand. And this was a bit surprising, because I had looked at the code previously, and I didn't find it that bad. But it turned out the reason was, of course, that even if you wrote a piece of code yourself today, 3 days later, it looked completely different, because 5 other developers had been working on it in the meantime. The final thing that they told me was that they spent a lot of time merging different feature branches. And if you have a look at that diagram, you see that, no, they didn't have a merge problem. Their problem was that their architecture just couldn't support their way of working with it. So please, align your architecture and your organization. Your code is going to thank you for it. Now, remember that project I just told you about, that they complained a lot about the defects. And indeed, they had a huge backlog of defects. And this shouldn't really come as a surprise, given what we actually know about software bugs. It turns out that the number of programmers behind a piece of code is one of the best predictors of the number of quality issues that code will have. So if we know about that correlation, I start to think that, yeah, again, this is something we can actually measure. This is data that we have in our version control history. So let's see if we can find a way to identify code at risk for defects. Here's one approach. This is a visualization called fractal figures. Fractal figures work like this. You consider each file in your system as a box. And each programmer gets assigned a color. And the more that programmer has contributed to the code, the larger the area of the box. Now, you see an example here from a real code base. And if I was after excess parallel development, I would go after the second one there, because that file has contributions from lots of different programmers. And when you find code like that, you need to inspect it and understand why. And I promise you, what you will find most of the time is that code changes for a reason. The reason that file attracts that many developers is probably because it has many reasons to do so. It has too many responsibilities. So fractal figures are a good starting point here, but we can do even more. If you look at the fractal figures, you will see that they actually give us a pretty good way to identify the main knowledge owner behind each piece of code. The programmer who has made most of the contributions. They are also probably the ones who know the most about that piece of code. So if we have that information on each file, again, why not aggregate it and project it onto the static surface of our code? That would allow us to build up a complete knowledge map of our code base. Here's what it looks like. Now, this is again real data from a real code base. This is the development of the programming language Scala, a part of the compiler here. And it's the same principle. Each file is visualized as a circle in this case, and each developer, the knowledge owner, is visualized by color on the corresponding circle. Now, a knowledge map is something that you can use to simplify communication. So let's say that we want to join this project, and we want to make a contribution to the backend in the upper corner there. Now, using our knowledge map, we see that the yellow developer has made most of the contributions. So she probably knows a lot about that code. And if she doesn't know, we see that that pink-orange developer has also contributed a lot to the backend. So let's ask him instead. But instead of focusing on individuals, we could get even more interesting data if we aggregate that information into teams, because that would actually give us a way to evaluate Conway's law. Here's what it looks like. Now, each color represents a team. And you see that from the perspective of Conway, this actually looks quite good. You see that the red team, they pretty much have their own subsystem where they could focus their efforts. And the pink team, they also have their own subsystem where they can work in isolation. But down in the corner, we have a large subsystem with contributions from all 3 teams. And again, when you find something like that, you need to understand why. And the reason may be as simple that this organization just lacks a fourth team to take on a shared responsibility. Or again, code changes for a reason, too many responsibilities, and perhaps that piece of code is better off split into 3 different parts. And of course, once you have that data, you can overlay it with the results of a temporal coupling analysis. Remember the project I told you about a while ago? The project where a simple change took 1 week because it rippled through the organization. That's how we found out. Now, the final part I want to show you, by tying back to the communication diagrams, the social networks. When we talk about social networks, we need to mention the Pareto principle as well. The Pareto principle is better known as the 80-20 rule. And it's something that holds true across all social networks, Facebook, Twitter, and I also found that it holds across code bases. That 80% of the content is created by 20% of the members. And you do have that in code as well. You have some developers that's been around for a long time in every system. They know the code inside out. Perhaps they are you. So what would happen if you would leave? If you would leave your current code base? Well, you would obviously get a knowledge gap. How big? Most of the time, we have no idea. But using this data, we can actually find out. Here's what it looks like. Have a look at those red areas. In this case, they don't represent any hotspots. No, they represent abandoned code. That is, code that's written by a developer who's no longer part of the organization. And this is something you can use to reason about the knowledge distribution in your code base. And when you do that, you will most probably find patterns like this, where you have an entire abandoned subsystem. And again, this is information you can use a bit more proactively as part of your risk management. So if you know that you plan to make some changes to a feature that's abandoned like this, use that information to schedule additional time for learning, because it is a hugely increased risk to modify code that we no longer understand. So I'm almost done now. I just want to sum it up for you. Today we have seen how techniques from forensic psychology can help us identify hotspots in code as well. And hotspots are code that helps us predict code that's hard to maintain and code at risk for defects. And we've also seen that once we embrace the past of our code base, its evolution, we get a lot of social information as well that help us measure things that we haven't been able to measure before. Things like knowledge distribution and knowledge loss. And I think it's important that these techniques, they don't stand on their own. They need a vital ingredient. They need you. Because these techniques are there to help and guide your expertise to where it's likely to be needed the most. And this is a huge topic. And if you want to read more about it, I do write a lot about it on my blog. Of course, I also have the complete book if you want to dive into the details. And the thing I'm working on right now is to provide these tools as a service. So it's something I hope that I will be able to release next month. If you're interested, sign up for a preview right now. It's free. Now, before I take questions, I'd like to take this opportunity and say thanks a lot for listening to me, and may the code be with you. Thanks. Oh, cool. Thanks. So, I got a bunch of questions here. First question is fascinating, but do you think you're confusing causation with correlation? No, I don't think so, but it's always a risk. And I'm not sure if that question refers to the my study there on the bugs. Could be so. The thing is that I base virtually every one of these analyses, I base it on empirical data. Because it turns out we actually have a subfield in academia that studies software evolution. So you have a lot of academic studies of really high quality that goes into most of those findings. So if you're interested in that, I have a lot of references in my book. So if you're interested, drop me an email. You have my email address there, and I'll be happy to provide you with some references on the supporting research material. So here's the next one is really interesting. How do you account for engineers changing teams over time when analyzing teams? Yes, it's a tricky question, and the way I do it is that I don't. When you do this analysis, one of the hardest things is to understand which time period that you should actually study. So what I tend to do is that I always, for the technical analysis, I always tend to run on the complete lifetime of the code base because it allows me to spot long-term trends. I also tend to run much, much shorter analysis, like the last sprint or the time since the last release or something like that. And this gives you, again, a different view and a different perspective that really, really helps you, particularly since all the stories and features you worked on are fresh in your mind. So you can see how it actually impacted your code base. And when I study the social metrics, I make sure that I don't go further back than until the last major organizational change. So that's basically how I do it. I think it would be too tricky and too much risk for bias otherwise, actually. Yeah, and that's the next one. How do you account for people switching teams? Again, a shorter analysis time span, but sometimes if it's just individuals that rotating, I just leave them in there, and you will see that as the example I showed you, where I have this line across different teams. That's not necessarily, most of the time that's a good sign, but even if you have heavy dependencies between your different teams, it's not necessarily bad, as long as you have a plausible explanation for it. I think that's the most important thing with all of these analyses, is that what you want to look for are the things that surprise you. As soon as you find something where you don't have a good explanation to why it looks the way it does, that's usually a warning sign. In your experience, how effective have you found TDD and unit testing to be in preventing defects and enforcing code quality and structure? Do you recommend TDD? Wow, I love that question. So, yeah, a lot of teams, part of my day job is I go to a company, I make an analysis of their code base, and I leave a report with findings and recommendations. And a lot of teams today, they use TDD or at least work a lot with automating tests and checks. And what I found out is quite interesting. I don't have any data if TDD actually helps you or not. There are other studies that look into that. And I would say that the findings are, I think they are still inconclusive. There are positive side effects to TDD, definitely. But what I tend to find is that most of the hotspots tend to be in the test code. The worst offenders are always in the test code. And I think the main reason, and I'm speculating now, but I think the main reason is that we developers, we make a difference. We make a mental divide. On one hand, we have the application code, and we know it's vital and important that we keep it clean and nice and maintainable and all that stuff. On the other hand, we have the test code. And most of the time, we're happy if we get around to write any of it at all. So, and I think that's a dangerous fallacy, because from a maintenance perspective, there's really no difference between your test code and your application code. If your test code lacks in quality, it will hold you back. And again, that amount of hotspots in test code is something I've seen independent of TDD or not TDD. So those were the questions I got here. And I will go over to the speaker clinic in case you want to continue the discussion. And I'll be happy to answer any questions you may have. So again, thanks a lot and enjoy the rest of the conference. Thanks.